Okay, recording started. Welcome again. Now I need to share the screen. And here it is. Good. Okay, so first, I booked the exam date in agreement with the other teachers. They will teach after me. And our proposal is as follows. Just a second to get the calendar for June. It's here, April, May, June. Okay. So we cannot make any exam up to, we cannot record any exam up to June 13 because it's the last lecture day. So we booked the first exam for June 17, 9:30. I know that some of you have to leave for Erasmus, and if there is any of these needs, just let me know. Last year, I had the permission from the university for the Erasmus students, only for the Erasmus students who already went back, to make the exam online. So I was already contacted by one of you having this need because I know that some of the Erasmus mid of June are leaving. So if you have any of these needs, so if you would like to take the exam online, because after mid of June you already left, let me know. I have to ask permission. We will find a solution. So if the solution is not exam online, maybe an exam earlier, and then I record later. Only for Erasmus students I can do that. So once again, if you have any of these needs, because June 17 is too late for you to be in presence in Bologna, let me know, okay? Because I have to ask permission for any of these students. So June 17 will be the first exam. It is in physical presence. It will be in the campus, in the other campus here in Bologna, located in Via Terracini. It's called Campus Bertalia or Lazzaretto. Because we need a lab in order to make the exam on the PC. You know that the exam will be a quiz. We need a lab, and the lab is booked there, okay, June 17. Second call will be just 1 second. Will be second call will be 1 second. I think it is beginning of July, but let me check. Okay, it's I need to confirm. I think it is July 2nd, okay? And then let me check. Let me check when is. There is a third date in July, and it's. Sorry, it's July 1st, which is a Tuesday. Okay, I found it. So first call June 17, second call July 1st. It's a Tuesday. It's these calls are scheduled at 9:30 in the morning. They will take about 2 hours. Okay, just for you if you need to plan other exams, etc. So,
Et du coup, on est que par 40, donc c'est bien qu'on discute un peu.
can you please,
Je vais être dans la coloc et je vais beaucoup me faire des postes.
okay, So there was a micro open. Third call, July 15, again Tuesday. I will put the dates in my website. They are not still there. They are not yet there. Okay. So again, June 17, July 1st, July 15, 9:30, Via Terracini, Campus Bertalia, Lazzaretto. And then there is a call in September. Let me give it to you. Just 1 second. It is September 11. It's a Thursday, September 11, 9:30. Okay. These are the first 4 calls. Okay. Any question? Okay, perfect. Another communication. Today, I need to leave at 3:30. So we teach from now to 2:45 as planned. We make only 10 minutes break, and then we make from 2:55 to 3:30. Okay, 3:30. Sorry, I have to take a train. You see my suitcase just beneath the table, under the table. Okay, good. Any question? No questions. Perfect. Now, let me share the screen. Oh, no, it's already shared. Thank you very much. So, last time, a very short recap. We started talking about the science of climate change, and we started talking about the forcings. And in particular, we talked about the emissions and energy from the sun. So you remember we explained, we mentioned that sun is the only source of energy that reaches the Earth. The Earth system is a closed system. What do we mean with closed? It means that there is no matter coming in or out, with the only exception for energy. It's a matter that comes in. And also there is some energy radiation from the Earth to the space. And another possibility to exchange matters with the space is related to meteorites. So the Earth system is closed. So no exchange of matter. What do I mean with matter? Masses, energy, fluxes of any physical quantity. So if I think about water, the Earth system is closed. No water from the space, no water out. So the global mass of water into the Earth system is conserved. Okay, so there is no loss of water, and there is no entrance of water. So the Earth system is closed with only 2 exceptions. Energy comes from the sun. It's the only source of energy for the Earth system. And maybe meteorites, asteroids. We know that this is possible. We know that, it is an hazard to which the Earth system is connected. So we talked about these 4 things, energy from the sun. And another relevant forcing for the Earth system is, as I said, the CO2 emissions. Emissions from humans, not only CO2, emission of greenhouse gases. This is considered to be a relevant forcing. And so this is why I am mentioning it explicitly. There are many other forcings originated by humans and originated by nature. You can think of volcanic eruptions. You can think of modification of land use. It is a forcing by humans on climate, and therefore they need to be considered by the science of climate. But you know that it is considered the CO2 emissions, in particular the human emissions in general, are considered a relevant forcing. This is why I showed to you these scenarios for human-induced emissions in the future. The business as usual scenario, which is The upper one is the more pessimistic. It's considered to be overly pessimistic, at least up to 3-4 years ago. And now, with the current geopolitical situation, it is becoming more difficult to predict how society will evolve in the future. The fate of decarbonization is more difficult to predict. But still, this is considered, the business as usual is considered overly pessimistic. And then there are the other scenarios, current policies, which I remind you predicts that we may reach a cap around 2040. And some scientists are convinced that we already reached the cap, which means the top of our emission. And then, of course, with decarbonization, we predict that the emissions will go down. And then there are the other scenarios. This is why we dedicated some space to it. We are discussing about these drivers because we want to set the basis to try to understand how the climate system works in order to provide an introduction to the science of climate change. So these are considered to be the most relevant forcings. Of course, energy from the sun is also affected by variability and may cause warming cooling because it is something that we know only from a small part of it. So the dynamics, the cycles of the sun, of the energy from the sun, the cycles of solar radiation, we know only a little. We know that there are some cycles, and if you're interested, you may study, for instance, you may have a look at the Milankovitch cycles. We know that there are 11-year cycles due to the sunspots, but we still know very little about solar emissions and its variability. It is, of course, a relevant forcing for the temperature over the Earth. And for instance, we are still looking for an explanation about the glacial ages that we had for the glaciations that the Earth experienced. And one possibility is a change in solar radiation. Other possibilities are a change of inclination of the Earth's axis, etc. Okay. Now, another important issue to set the basis for the science of climate is given by the feedbacks. What are the feedbacks? The feedbacks are kind of reaction of the climate system to a perturbation. So when there is a system in equilibrium, if you cause a perturbation, the system normally reacts by trying to reestablish equilibrium. It's like our body. When we get a shock, there is a reaction of the body which tends to recover our health, our good health. And the same for any other system in equilibrium. Nature is a living system, and if it exists, we already discussed it, it's because indeed it's a resilient system. Resilient means that the equilibrium is a stable equilibrium, it's a solid equilibrium. And therefore, we may expect that the climate system, if perturbed, reacts by trying to keep its equilibrium. But on the other hand, you have to remember two things. First, that even the most solid equilibrium can be broken. Like for human health, we know that sometimes when we get a shock, we try to react with medicines, but on the other hand, they have side effects. So it may happen sometimes that if you sum to the initial perturbation a side effect, you may get to a worse state. With respect to the shocked state, you may get in a worse situation. And this is because you have a side effect, which is a feedback that doesn't help. On the contrary, it's a reaction of the system, a reaction also of the healthcare system that causes a deterioration, a further deterioration of our health. And the same may happen for nature. So it may happen that, nature reacts, but the reaction brings the whole system to a more deteriorated state. This may happen. So first thing is the feedback. We expect that it's a good feedback, but the feedback may also be a negative, negative is not the right word, a bad feedback. I will explain later why negative is not a right word. This is the first consideration. Second consideration, a natural system may have two equilibrium states, or more than one, let's say. So it may happen that the system keeps the equilibrium, but in a different state. And the different state may be a state that it's not so favorable to humans. Of course, the current equilibrium of nature, it's also not favorable to humans. We already discussed, and nature is difficult. It's an hostile environment. But during the millennia, the humans have adapted. So they have shaped the natural system in a way to make it more livable. Think, for instance, of the region here. It was an unhealthy region in its natural condition because it was a marsh. And you know that marshes are unhealthy environments. And then the humans drained it. So the humans, again, in the years and in their history, adapted to this equilibrium state. And therefore, if the nature goes to another equilibrium state, I will make examples, then humans are discomfortable because they need to adapt to a new equilibrium state. So, I mean, feedbacks are important to be understood. And let me give you some examples. For instance, you see the figure here. First thing, we call, if we make reference to global warming, the figure makes reference to global warming. So you can start from this process, global warming. And I need to ask you a favor because I can teach if somebody is speaking because I can listen perfectly what you're saying. Sorry, I can teach if somebody is speaking because I can listen perfectly what you're saying because it looks like the room is the thing that nobody listens to you, but I can listen. So please don't speak. Really, this is a limitation for me. I apologize, but I can teach if somebody is speaking. Okay, if you need to speak, it's not a problem. You can leave the room and then come back later. Okay, global warming. Let's start from here. Global warming gives some consequences. For instance, let's focus on snow cover loss. Snow cover loss means that you have a reduction of reflection of sunlight. This means that part of the sunlight that was previously reflected back to space now is absorbed by the Earth. So it is a further contribution to global warming. So you start from global warming. The feedback is an exacerbation of global warming. It's a further increase. And another feedback that increases global warming, increase the concentration of water vapor into the air. The water vapor is a greenhouse gas. And therefore, further exacerbation of global warming. These feedbacks that reinforce the signal are called positive feedbacks. So this is why earlier I said negative, positive. I made a wrong, I used a wrong terminology because a positive feedback is a feedback that reinforces the signal, which is not good because we have a perturbation, global warming, and then the reaction of the Earth system is to increase this perturbation. So it's not a good feedback. So remember that positive means not good. Okay, another example is melting permafrost. Melting permafrost releases methane into the atmosphere. Methane is a powerful greenhouse gas. And therefore, we are much concerned by the emissions of methane. From the oceans, for instance, with the warming ocean, there is an increased emission of methane from the oceans. Again, from the warming oceans, I mentioned last time, there is an increase of CO2 emissions from the oceans. And these are all positive feedbacks. These tend to deteriorate even more the situation. But we may have also, after global warming, negative feedbacks, which stabilize the system. Examples: warmer Earth radiates more heat into the space. If the Earth gets warmer, we have more radiation of heat into the space, and therefore it's compensating global warming. Another example: plants with more CO2, you have more CO2 is a natural fertilizer, and therefore we have more vegetation growth. Vegetation growth means that we have more removal of carbon dioxide. So forests are known to be a carbon sink. Carbon sink means that they absorb CO2. They contribute to reduce CO2 emissions, CO2 concentration. So if you a carbon sink, by definition, is a storage of carbon, so it's a carbon removal from the atmosphere. Third example: oceans. Oceans remove carbon dioxide from the earth, and from the air, sorry, and therefore they can act as a negative feedback. On the other hand, we know that with increasing temperature of the ocean, so anyway, if the ocean remains at the same temperature, there is an increase of the storage of CO2 storage into the oceans, because with an increased concentration in the atmosphere, then we have more difference in concentration between atmosphere and oceans, and therefore some carbon is transferred additionally from atmosphere to the oceans. On the other hand, if the ocean increases its temperature, we have also increased flux of carbon from the ocean to the atmosphere. So it is to be understood, depending on the dynamics of the temperature of the ocean, if the overall effect is a sink of carbon or an increase of emissions. So these negative feedbacks, on the other hand, are a good thing, and they act against global warming. Global warming, which is caused, and you see on the top of the picture, by the global concentration of greenhouse gases. Feedbacks, you understand, are extremely important for their action, positive and negative. And the problem is that we have still a limited understanding of these feedbacks in the climate system. So we need to set the basis of climate science, of course. We need to include these feedbacks, but our current understanding is limited to only a part of them. Okay. So this makes feedbacks extremely interesting. And now I go forward with some slides to anticipate the discussion about tipping points. So I mentioned earlier that the Earth system, the nature system, may have more than one stable equilibrium. So what is a tipping point? A tipping point is the transition between one stable equilibrium and another stable equilibrium. So basically, it's a state of the system that it's on the boundary. And if the system gets to a tipping point, it means that with a small perturbation, it's like getting over the top of a mountain. With a small perturbation of the equilibrium, one can fall on one side of the mountain or the other side of the mountain. So if we get the Earth system close to a tipping point, with an additional small perturbation, we may get into a stable equilibrium or another stable equilibrium. So these tipping points, you understand, are a matter of course. And I'll give you an example. For instance, forests, if you clear cut a forest, then you get to an area that is unvegetated, and therefore the next step, if the climate permits, if there is enough water, is a regrowth of the vegetation. But we don't start from scratch with the trees. We start with brushes. First is grass, and then brushes, and then trees. But the step between brushes and trees is not automatic. If there are favorable conditions, we get again back to the forest state. But it is, as I said, it is not automatic. In fact, what we do usually when we want to convert brushed areas, an area with brushes, to a forest, what we do is to cut the brushes and leave there only the young plants, the young trees, in order to avoid that brushes compete with trees, because brushes usually are stronger. The reason why they grow before than trees is that they are more resilient vegetation, and therefore, being resilient, they compete with the trees. They try to keep their position. So basically, if you clear cut a forest and you don't do anything later, you end up in a different equilibrium state, which is brushes. Okay? Or, for instance, another example that I may give to you, which is very interesting, extremely interesting, is the RLC disaster. Let me just open over the web, Google. Okay, you got here RLC disaster. And you may already know something about that. Let's go to, there are a lot of links, but let's go to Wikipedia. Also, National Geographic is interesting. You see the title here, what the RLC might teach us on life after environmental disaster. This is a picture of the former RLC. You see what happens here, both left there, okay? And if we go to Wikipedia, which is interesting, let me see Wikipedia. Let me search for Wikipedia. RLC, yeah. Just a second. Okay, you see a figure here. This is RLC between 1989 and 2008. Its water is gone. And keep in mind that 1989 was already starting to dry up. So why is this? So first of all, it's the RLC was really huge, and since 1960, it started shrinking, and now 90% of this area its area is gone. Why? Because the former Soviet Union started to take water from the tributaries to irrigate cotton. Cotton is extremely water demanding. Cotton was, of course, an important production. And therefore they started to take water from the tributaries, and then the lake started to shrink. But they didn't realize that shrinking was going to completely dry the lake. They realized that only later on, when it was already too late to recover, because with the reduction of the lake surface, more than 90%, evaporation is also decreased, and therefore now they have less rainfall. So even if they now stopped to take water from the rivers, there is less rainfall, there is no water in the rivers anymore. Or let's say there is less water in the rivers. So getting back to the original situation turned out to be impossible. And therefore, you get this new equilibrium state. And let me go to the page of National Geographic. This is the new equilibrium state. So a desert area, basically, because also the RLC had a high salinity, and with the dry up, the area, the land became extremely salted, and therefore also the growth of vegetation in a salted area with reduced rainfall becomes a problem. And so this is an example where from an equilibrium state that was a lake, they turned it into another equilibrium state. And this is considered to be one of the most relevant environmental disasters caused by humans, to give you an example. And it's an example of a tipping point. So let's go back to our slide. Tipping points may be reversible or not, and they are maybe caused by feedback, positive feedbacks that bring us on the other side of a tipping point. And so what is an example of tipping points, for instance? Or let's say, what is an example of what we believe would be tipping points? Because the problem is, read the last sentence, the IPCC, which I already mentioned to you, is one of the most authoritative panel of experts on climate at the global level, states that the precise level of climate change sufficient to trigger a tipping point remains uncertain. And therefore, these tipping points are not included into climate models. We scientifically, we don't know how to treat them. Let me give you some examples. We believe that these are possible. So the Sahara greening, we know that Sahara was originally a green region, and now it's a desert. So what caused this change, this transformation? We don't know. And other examples are a change in the West African monsoon. Another example would be the dieback of Amazonas rainforest, because, as you know, we are clear-cutting part of the Amazonas, which is, on the one hand, probably unavoidable with the increasing global population. But what if there is a tipping point? What if the Amazonas can survive only with a certain extension? What if there is a limiting extension for the dieback of the Amazonia? And the instability of the ice caps. So we have the concern that ice caps could melt suddenly. And this is why people are trying to study what happened in the past when we turned from ice caps to no ice caps and vice versa. And the scientists are in particular trying to understand whether the change has been rapid or not, because it may happen that indeed there is a sudden melt of the ice cap. Why? Because we discovered recently that in the body of the ice caps, there are a lot of buried lakes, and these lakes are much extended in volume, a lot of volume. And the reason why there is water encapsulated in the ice is the pressure. The high pressure of the ice cover makes water in liquid phase even below 0 degrees. And you know that in the body of the ice, anyway, the temperature is not much below 0. And therefore, what is the concern? The concern is that with the reduced thickness of the ice, we may get to a point where suddenly we get an outburst flood of water from these lakes. And we know that some of them already occurred. But how many lakes there are in the ice caps and how deep they are? So there are a lot of research projects trying to understand the geometry of these lakes, their volume, and there are some research projects that are trying to take videos of a glacial outburst. So they put cameras where they believe that there are lakes that are quite close to the surface, with the hope that they can take a video of what happens during a glacial outburst. But still our knowledge is very limited. These lakes were discovered, and most of them were discovered very recently. Okay, so these tipping points, once again, are the reason of our uncertainty, and in practical terms, are the reason of our concern, because, of course, if we cannot really understand them, it means that we cannot predict them. So we get predictions of future climate, we set the basis of science of climate change, science of climate, in order to elaborate these predictions. But on the other hand, there are unknowns, and therefore these predictions may be overly pessimistic or overly optimistic. So, for instance, when we predict the increasing of sea level up to 2100, our models, the most pessimist models, predict a further increase of about 30 centimeters from now. But they don't include the possibility that the ice caps suddenly melt. If the ice caps suddenly melt, suddenly get transformed into water, then we are talking about an increase of sea levels of several meters. It's a different story, but unfortunately, for us, it's difficult to make a prediction. So I go back with the slides. So before we get into the details then of how we try to set the basis for a theory for a science of climate change, let me give you an example of some examples of research questions. And a very relevant research question is climate change attribution, means to recognize to what extent humans are responsible for the recent climate change, in particular recent global warming. As you see in the animated figure, this is a figure showing the map of global warming and the progress of global warming. We already talked about this research question. So climate change attribution is a central topic in climate science. So we develop a science of climate because we want to try to give an example to climate change attribution. And it's not simple because in the past we know that we had climate changes much larger than today. We already learned that also the pace of global warming is comparable to what happened into the past. It's true that global warming in the past 30 years is rapidly increasing, but it's not something really unprecedented. It's something that already occurred. Already in the past, we had examples of very rapid changes. On the other hand, it's also true that there is, evidence. There is, let's say, a physical support, a theoretical support, a scientific support to the human influence. For sure, the humans, like any other living species, contribute to global warming. On the other hand, the big question is the relevance, the importance of the human contribution. And indeed, there are physical laws telling us that this may be relevant. But until we fully know the natural variability, this remains a challenging research question. And also it may depend on the local context, because it may depend on local configuration of the land. For instance, if we think of the cities, we already discussed the urban in Thailand, it's clear that humans in the context of cities, of big cities, contributed to local warming a lot, more than other causes. This is clear. But it remains a challenging research question. And in my tutorials, lecture notes, there are some links of videos which explain to you what is the support, examples of support to the human cause. And there is also, as you see linked here, an interesting video that talks about the changes of climate that we had in the past. And when I say in the past, look in the very far past, because to say that the Earth was never so warm in the past 2,000 years is not so significant. And we know that. We know that in the past 2,000 years, we didn't have this high temperature, or let's say, we got quite close in some periods, but not so high temperature. But 2,000 years is nothing for the climate system. In geological terms, it's nothing, 2,000 years. And we have to go back more in the past. I will show you some graphs for the recent increase of temperature and what we know from the past. But these videos are interesting. We don't watch them now because they are quite 6 minutes long. So it's something, if you're interested, that I suggest you to have a look if you're interested, but on the other hand, we don't look at them now. So this is an example of a research question. Now, we already mentioned that the concerns about climate change are quite dated, and sorry, made a mistake. And so let's skip this. And now let's try to look at in more details at the scientific basis. So let's get into the core of our discussion. And first, okay, it's a very important topic. It has relevant political implications. And you may have heard the recent development after Trump's election. Now in the United States, there is a pushback against climate science because of political implications, which on the one hand, they are motivated because I already mentioned to you that decarbonization has high social costs. So when we get in a difficult situation, in a difficult international situation, of course, we have to set priorities. And currently, in the situation we are experiencing now, let's say that climate change is less of a priority with respect to 10 years ago. Because 10 years ago, still, we were dreaming of being able to concentrate our resources in a global liberal development. And today, the situation is very different. Today, we are kind of seeing that there is an awareness of the politics that in order to ensure a peaceful future, we need to increase the expense into the arms, into the military expenses, and therefore it means that resources are not infinite. So if you put money on a new priority, you have to revisit the former priorities. But indeed, it remains a politically relevant issue. And from the scientific point of view, which is what is more interesting for us, because we are discussing about science and not about politics of climate change. It's not a negative thing when talking about politics. It's a positive thing because politics means the management of public resources, but we are not talking of it, okay? So from a scientific point of view, it is a multidisciplinary problem. It is a multidisciplinary science. And let me try to better understand the meaning of multidisciplinary, interdisciplinary, and transdisciplinary, which are three terms that I think are interesting to know if we want to look at the future of science. So we say that a problem is multidisciplinary when to find a solution requires the contribution of several disciplines. And this is multidisciplinarity. You get results from engineering, results from climate science, results from social sciences, results from political sciences, and you put them together in order to identify a solution. This is multidisciplinarity. And then there is interdisciplinarity. Interdisciplinarity is some more than putting together results. Interdisciplinarity is integrating several disciplines. It means that you get engineers, social scientists, political scientists, climate scientists to work together and to find together a solution. So it's not putting together the results, it's putting people together to work on it. So interdisciplinarity is more ambitious. It is extremely difficult. Multidisciplinarity is relatively easy. Interdisciplinarity it is extremely difficult. Why? Because these people are not working in the same lab. So first of all, in physical terms, you have to move these people to work in the same lab, which is not easy because moving people is not easy. It is something that may be easy if you plan to realize it in like 30 years. But if you simply want to put people working in different environments to work together, so from a physical point of view, it's not easy. It's not easy because of terminology. I'm not sure whether you come from different disciplines. try to speak, and you see that the terminology is different. So when you say use a term, an engineer means something. And for instance, if I say probability, a statistician usually gives a mean to probability, which is based on a rigorous definition, Kolmogorov axioms. As an engineer, I tend to use probability to express a likelihood, like it is probable that the result is this. I mean, it is likely. It is a different story. And you may say, you may think that this is a minor problem. It's not actually, because when you have a background, a full background developed in your studies and your PhD and your career, using some terminology, and you are used to talk in some terms, to use methods consequently, it's not easy to change the terminology, to change the methods. And then there is a third problem that is probably even more relevant. So scientific assessment, evaluation of scientific results is generally disciplinary. In fact, some funding agencies discourage researchers to put together interdisciplinary proposals because it's difficult to find people who evaluate them. And once again, you may think, what kind of a problem is this? We just need a reorganization. It's not easy because, for instance, the career of a university professor, the career of a researcher is based on periodic assessments. And if the researchers that get interdisciplinary fail, they don't move forward in their career, they stop working. But changing this system of scientific assessment requires a modification of the laws, requires a reorganization of scientific associations, which try to resist because nobody want to change. So when we are part of a system, usually we are concerned about changes, because changes, require an adaptation. So I think that indeed the assessment system of academic and scientific progresses is a major bottleneck to interdisciplinarity. And then there is transdisciplinarity. What does it mean, transdisciplinarity? Probably you don't listen to this term very often. Transdisciplinarity means that these people working together, they generate a new discipline. They generate a new discipline. So basically, we start from hydrology, from climate science, from politics, socioeconomics, and generate a new theory which borrows something from the different disciplines, but generates new models. They are not integrated models, are new models based on a new theory. And this is the most ambitious target that we need to achieve if we want to promote a really improved knowledge. Really improved knowledge. So I may give you an example. And the example is related to interdisciplinary work between water scientists and statisticians. Usually, we use the results by statisticians in order to analyze, assess uncertainty in water science predictions. And these people are not working together. We just take the books on the statistics and we borrow the results. Actually, what I think the water scientists need is not just something for modeling uncertainty, but something to understand uncertainty. So they need to put together physics with statistics like they did in quantum mechanics. In quantum mechanics, they generated a new theory, the theory of quantum mechanics, which is quantum statistical mechanics. The father was Niels Bohr. And he generated a new theory by putting together a statistical description of the position of the electrons. The same thing would be needed in water science today, a new theory explaining the formation of water flow to describe the displacement and fluxes of water over the Earth that incorporates the theory of physics. Of course, it's movement of a body, so it's physics, and statistics, and possibly chemistry if there is also a problem of water quality. So transdisciplinarity is what we need, but it is an ambition. It's anyway important that you try, that you know these terms, I think. Okay, so we are talking of a scientific issue and scientific questions that are extremely popular. Extremely popular means high priority, means also opportunities. Because when you have a science that is still poorly known and it's extremely needed, it's an opportunity, both for professionals and for researchers. So this is why also climate, science of climate is today so important. Okay, I think, yeah, let me just talk about the role of engineering, okay? And engineering is just one of the many sciences that are involved into climate science. Why engineering? Because you actually, it's not so known that engineering has a relevant role in climate science. But why engineering? First of all, because engineering is related to solutions. Finding solutions to the climate problem may require solutions in terms of reduction of emissions, like clean energy, and clean energy is it's in the realm of engineering, of energy engineering. May require also solving the climate problems, may require adaptation. Adaptation means infrastructures like water supply system, like artificial reservoirs. Again, it's in the realm of engineering. Actually, currently, there is still a separation between what are called the purely scientific branches of science, like physics, mathematics, climate science, and engineering. There is still a separation because engineering is considered to be technical, so in charge of the technical development. But it's not considered a science that gives a significant input to physics, to climate, etc. In some of the cases, I could also perceive that it's even not considered a science. It's considered something related to technology, engineering. Actually, this dichotomy between science and engineering, I think it's one of the causes why we didn't move forward in addressing the climate change problem. Because we didn't move forward because when it comes to solutions, we get into the realm of engineering, in the domain of engineering. And if engineering is not involved in also in the development of the theory, starting from, for instance, the estimation of the future emissions, it becomes very difficult later on to converge over suitable solutions. And therefore, I think that, of course, I am biased because I am an engineer, but I think that we need a more integrated cooperation between pure scientists and engineers. And this is also why recently engineering has shifted a little bit from application towards the scientific investigation. I think we should try to promote a better integration of engineering and medicine, climate science, etc. Again, it is not easy. So here you see some examples of research questions, more detailed with respect to the first one that I mentioned. I mentioned climate change attribution. Here, these questions are more detailed and are more related to engineering specifically. So interaction between human-induced climate change and natural climate variability. It's in between climate science, statistics, and engineering. Uncertainty assessment of climate simulation for the sake of engineering design. Of course, why do we need uncertainty assessment? Because we need uncertainty assessment in the design phase. When we have to size an infrastructure, we have to estimate the risk of failure, and therefore the risk of failure here is related to uncertainty assessment of climate predictions. Usually, climate scientists tend to give low weight to uncertainty assessment because it doesn't help, in their opinion, to clarify their message. Actually, when it comes to solution, it becomes essential. The capability of climate simulation to reliably reproduce the frequency of extreme events, therefore avoiding underestimation of extremes. This is in the realm of hydrology, which is intersecting with engineering. Capability of climate simulation to estimate the risk related to the so-called black swans, unexpected events. This is again engineering, and estimation of design variable for climate action. This is typically an engineering task. Okay, let's move forward to setting the basis. Tipping points, we already discussed them. And I forgot to mention these second slides and tipping points. These are social tipping elements, tipping points of societal organization. Just have a look here, because it is interesting. I mean, also in our societal organization, we may have tipping points. For instance, one typical tipping point is the default of a country, of a sovereign country, economic default. It changes, it causes a big change to another equilibrium state. And so, for instance, other tipping points are related to technology, to governance. And these are probably more easily understandable with respect to the tipping point of climate, but they have also to be considered. For instance, one thing that I often say is that the effect of climate change is the impact of climate change, the impact of flood events, drought events, depends on the public debt of the country. If the country has a huge public debt, then recovering from a shock is more difficult. This is obvious, but also the country gets more vulnerable because it doesn't have money to invest in protection, in resilience, in sustainability, and therefore makes the country more exposed to risks related to climate change. Now, what is another extremely important basis for a science? Data. So let's discuss about data, because this makes a big difference in our capability to improve this science of climate. Let me look at the chat 1 second. I want to make sure that everybody, okay. So data. I already mentioned that we don't have a long data records, and this is the problem. For some reason, I already mentioned to you this. For some reasons, the humans started very early to observe stars, probably because they needed it, but they didn't observe climate, which is very easy to observe. if you think of rainfall, for instance, but we didn't start until like 300 years ago. And what is the reason? I think that the reason is that they had other priorities, because climate becomes a priority when you are in a good stage in terms of societal development, welfare. And in the past, I think they had other priorities. So they started the stars because the people needed to get oriented in navigation, and navigation was extremely important in the past. It was the main vector for the trade of goods and for traveling. So this was a priority. And also it was a priority in terms of organizing the national defense, because also the national defense was relying on defending the sea, the coastline, and therefore navigation was an essential element. So in the past, indeed, the military priorities were ranked higher than in the last 70 years, at least in the Western world. And they had other priorities, like probably now we are starting having other priorities. But this is probably the reason why we don't have long data records. On the other hand, the scientific method relies on data. So we know the classical scientific method, how it's based. First of all, we observe something that we don't understand. Then we observe something. So we make observations. And then we postulate a theory to give an explanation. And then we make experiments to validate the theory. So you see that observing, so the experiment is important in two steps. First, the observation, and then the theory and the validation of the theory. In climate science, unfortunately, we cannot make experiments, or we can make experiments into the lab, but they are really different spatial scale, different temporal scale, so they are not really real experiments. It's not like studying the movement of a body where you can make real experiments. And unfortunately, we have limited observations. Now, we have plenty of information thanks to the satellites, to remote sensing, but the situation is relatively recent. It's very recent. So, how to solve this problem? And first, there is a first solution that has been proposed. Just 1 second for the next slide. A first solution that has been proposed is to use models, and therefore to validate the theory through model experiments, which is, I mean, it is fine. It's not a new procedure. So one formulates different competing models for validating a phenomenon. So I make the assumption that human emissions are responsible for global warming. I set up competing models, and then I see how many models provide support to this assumption. And we know that this is why we support our understanding about human influence. We say that models, the best of our models, cannot reproduce global warming unless we put human emission into them. This is not new. On the other hand, we have to be aware that it's not really what the scientific theory recommends, because, of course, any basically you use the result of a theory to validate the theory, because the model must be based from the theory, from an assumption. And then the model reflects our current understanding. It is missing feedbacks, is missing a lot of information. And therefore, basically, it's a circular process. We make a theory, we produce with the theory a model, and then we use the model to validate the theory. It is something that cannot be completely satisfactory. There is uncertainty in it. And another possibility is to use consensus. Okay, before moving forward, let me show you, because I forgot to do this. This is annual rainfall series in Bologna. Bologna is one of the longest daily rainfall series existing today at global level. It started in 1730, continuously from 1813, which means that every day from 1813 we have daily rainfall in Bologna, and this is the annual series. What you can see here in gray is the long-term droughts. Long-term droughts are something about quite concerning. We know that sometimes it happens somewhere that we see a drought, and this drought is lasting for more than 5 years. This is the definition of a long-term drought. More than 5 years, it's a lot and causes a big impact. And this is happening in many continents, and we don't understand why. So in Bologna, we can see some of these long-term droughts. The last one was between around 1950. And then in the past 70 years, we didn't experience any long-term drought. We experienced, indeed, significant droughts, but not long-term ones. So significant droughts, I mean droughts, seasonal droughts lasting 1 year, but not very long-term ones. And this is something that we can't explain. Maybe that global warming decreased drought risk. There might be several possible explanations. And this is something that clarifies to you what is the value of data. This is indeed an experiment. An experiment saying that it doesn't mean that here in Bologna, long-term drought risk is increased. This data are really valuable, but on the other hand, 200 years of data is nothing. Unfortunately, had we rainfall data from the time of the Romans, our understanding of climate would be completely different. I forgot to mention another possibility, because I said there are two methods: relying on models to confirm the experiment in absence of data, or relying on consensus. Actually, there is a third solution, that is to use proxy data like 3 rings to reconstruct past climate. So let me talk about this, and then I will mention again consensus and providing support with models. So proxy, there is a lot of research on the use of proxy data to reconstruct past climate. This is called paleoclimatic reconstruction, where paleo means before the instrumental period, which started conventionally in 1850. So from 1850, we have measurements of temperature in a sufficient number to allow us to reconstruct the global temperature. Now, what are these proxies? The proxies are observations that are not climatic observations, but contain information that may allow us to reconstruct climate variables like temperature, rainfall, etc. So what are these proxies? The most known proxy is given by 3 rings. 3 rings can allow us to get information which may date back to 15 years ago, 15, 16 years ago. Sorry, 500 years ago. 500 years ago, 500, 600 years ago. So, for instance, there is a European atlas that starts from 1400, so 600 years of data. Because this is the age of the oldest trees that we can find. So, by measuring the width of the tree ring, which is annual resolution, as we know, we get information on climate because a larger width means that in that year there was a more favorable condition for the growth of the tree. And more favorable condition means higher temperature and water, because this is what they need to grow. They need warm temperature and water. Of course, there is the problem that the resolution is annual, so we don't get seasonal information from here. This is the most popular proxy. It has the advantage that we have a lot of rings, a lot of information available, a lot of samples, more in more in the Americas than in Europe, actually. But also in Europe, we have some sample. Sample means an image like you see on the screen of the tree. Another very important proxy is given by the ice cores. And the ice cores basically are recovered with ice carrots. The length of the proxy is much longer, and the ice carrot may go deep into the ice for, like you see here, 4 kilometers. And then, by analyzing the layers of the core, we can get information for a very long time. And by looking at the composition of the layer, we can get information on amount of precipitation with the thickness of the layer, and also the composition of the atmosphere. Because, of course, the snow that fell over the ground captured some particles that were suspended in the atmosphere. For instance, we can get information about volcanic eruptions. We can get a lot of information. We will dedicate a specific lecture on that, on the analysis of the ice cores, because this is indeed very important. And another important proxy is given by coral reefs. Coral reefs, they survive, they develop in the very long time, and by looking at the composition of the reefs, we can get information on the particles that were embedded into the ocean, the composition of the concentration of substances in the ocean, and we can get information on climate. There are a lot of cruises that are still organized to get samples from the bottom of the oceans. Another important information is given by sediments, and in particular, lacustrine sediments into the lakes, because, again, they collect information about the surrounding vegetation, about precipitation, and so there are several proxies that can be used. There are interesting websites that you may consult because most of these data are publicly available. For instance, if you look at the, let's look on Google again. The Tree Ring Atlas. Okay, this is in particular referred to droughts. This atlas here is extremely interesting because it can be used to reconstruct local climate everywhere in a very user-friendly manner. Actually, I never used it, so I'm not really ready. But let's look, for instance, Russia. I think there is a part for Europe. Let me see. Okay, here it is, the Old World Drought Atlas. So, first of all, here you can see an animation which reconstruct the occurrence of droughts in the past, I think it is 2000 years, and the droughts are depicted in red. When you see blue, it means a lot of water, and when you see orange and red means water scarcity. And so, for instance, let's move forward. Around 1400, I think, in Europe, there was a huge drought. Here it is. Just 1 second. Around 1400, there was in Europe a strong drought. And you see that indeed the red color is dominant. It lasted for this very dry period, lasted for about 80 years. And we had several reconstructions confirming this very dry century in 1400 over Europe. And okay, let's stop this. And you see that here you can download the entire data set, and you can extract time series. So this is particularly for drought. PDSI is a drought indicator, and you can extract data for a region or a single grid point. And if you extract a single grid point, I think you get a map. Okay, it is not correctly loaded, but here you could put the signpost here and then create time series. Okay, now there is an error because probably here there are also some controls on the execution of automatic routines. I'm giving you this information because this could be also an interesting opportunity to get data for final thesis or whatever, or for producing a report. These are data that are readily available. And this is for drought, but there are also data for floods. Okay, what is the issue here? Let me just close this. What is the issue here? It's once again uncertainty. So proxy data by definition are more uncertain than direct observations. These are reconstructed data. And besides the resolution, that in most of the cases is annual resolution, there is also a problem of uncertainty. But on the other hand, these data are recognized to be a very important information for studying climate variability. And what comes out is that if you look back 1,000 years, variability of climate looks really larger than looking back only 150 years, which means the instrumental period. And this is something that is, of course, expected. The longer your sample and the longer the probability of finding extremes. So if you look at only climate for 10 years, it's unlikely that you find extremes. For instance, if you look at the Po River floods, if you look back 10 years, no floods. If you look back 20 years, no floods. If you look back 25 years, you find one. And then if you look back 30 years, you find two. If you look back 70 years, you find three. And with different magnitude. The more you look back, the longer the sample, and the better your knowledge of extremes, which means more variability. So this is something expected. On the other hand, it clarifies that indeed what we call natural variability, because if you go further in the past than 1850, 1850 was already before the Industrial Revolution, you get into a period where human emissions were not significant, were much lower than today, of course, before industrialization. And therefore, it's considered to be natural variability. And there is a lot of variability. For instance, if you look at this I-score data, it's not clear to me what is the extension in time, because I think the correspondence in depth, 1 meter should be something like including, let's say, between 50 and 100 years. So if 1 meter is 100 years, then here you go back 4,000 years in time, which is fine for, sorry, not for 400,000 years in time, which is fine for an I-score. Again, 400,000 years back. And you see that this is a proxy for temperature, the deuterium. You see that there is indeed a significant variability, which increases as you go into the past. And you can see also very different regimes. So regimes with a quite a stable situation, which lasted for maybe centuries, and then periods with a large variability. So indeed, the feeling is that the weather, the climate to which we were used during the instrumental period, being very short, it's a climate that was relatively stable. And if we go back into the past, we see huge variations. We will dedicate a lecture on this. And then here there is a discussion on using models. So, I already mentioned what is the limitation of this. Okay, now a few words to conclude this introduction, this preparation, and climate impact. This is another challenging research question. So, okay, climate is changing, but what is the impact? And here, again, we need interdisciplinarity, because we need to transform changes in a climatic variable into changes in a variable that is not climatic. Could be river flow, could be public debt, could be an economic variable. Because in order to estimate impact, impact is defined as risk, and risk that became true. And risk, it's usually measured in different units, but very often it is measured in economic terms. And therefore, climate impact, so for instance, the impact of flood, very often is measured in terms of damage. And again, here you need really to put disciplines again together, because it's not just enough to estimate a change in temperature or a change in rainfall. If you want to move to floods, you need an additional model that is transforming rainfall into river flow. And therefore, typically what we do, what scientists in general do, is to use a cascade of models. So we use a climate model to produce a future scenario, a future climate, and then this future climate is routed through a model that estimates the probability of flood, the flood hazard. And then, depending on the value of the affected region, which can be economic value, then we estimate the impact, the damage. Of course, not everything is measurable in economic terms, so depending on the impact, we have to estimate, we have to understand, to find a proper unit for measuring it. Now, why these two graphs? Because what you see in the upper graph is the losses from weather disasters worldwide from 1980 to 2018, 1990. and you see an increase of the damage associated to weather disasters. On the other hand, the lower graph shows the damage as a percentage of global GDP, gross domestic product. So here it's more stable. What does this mean? It means that probably the increase is motivated by an increased value. The damage is increased because for the same flood, you have a higher damage because the value of the goods that are affected by the floods is increased. So you really see that climate science is not everything. We need to put together several disciplines. And now I think we are ready for trying to get into the details because we discussed about drivers, we discussed about forcings, feedbacks, we discussed about tipping points, we discussed about data and several implications, and we discussed the need for a multidisciplinary approach. Now let's get into the basis of a theory, of a science explaining climate change, because this is our target. We will not be very detailed, very mathematical, but it is important that we understand the concept. And for moving forward, I need to pass to the next lecture. And do you have any questions so far? Not anything. Let me look at the chat. If you don't have any question, I prefer to anticipate now our 10 minutes break. So let's meet again at 10 to 3. Okay, good. Thank you very much. Okay. Just to remind you, we just concluded the second lecture note, setting the basis of climate science. I just want to show you, of course, the lecture note is much more extended than the PowerPoint presentation, as you know. And I just want to show you a couple of things here, which I think are interesting. There is a box, there are several links of videos, and there is a box which aims to introduce what are statistical computations, because we discussed several times that we need to compute statistics on climate, or at least statistics on weather, which are at least 30 years long in order to describe the climate. And we also talked several times about uncertainty assessment, and one classical way to assess uncertainty is through statistics. Statistics sometimes is considered to be a boring science. Actually, it's not particularly complicated, and it is considered to be boring because it looks complicated and it looks something like crunching numbers. Actually, it's not particularly complicated, and it's not only crunching numbers. Of course, it's also crunching numbers, but there is a lot of physical implications. So the purpose of this box is to give you some information, and in particular on an open software that has been conceived for statistical computation, but then rapidly extended to any kind of computation in science. It's largely used, this software in science, to make computation. It is like MATLAB, it is very similar, but it is open, while MATLAB, as you know, it's a commercial software. The software which is introduced here is open. It has a lot of support in the community. So I think it is a useful information if it happens to you that you need, because you are interested or because you are commissioned, you need to make statistical analysis starting from the very simple basic, like computing the average of a series of numbers. And you want to use something that is free and something that is high level. This is an opportunity, and here there is the link, as there is also a very simple example once that you install the software to draw a plot. The software is called R Project for Statistical Computing. Again, it's free, it's available on Windows, Mac, Linux. It is a useful information because in several of your disciplines you may need to make figures, to make statistical assessment, and usually what students do is to use Excel, which is fine. On the other hand, it's commercial and it's not very powerful, meaning that if you need to analyze a huge amount of data, Excel is a bit limited. This one is like MATLAB, it's less user-friendly with respect to Excel, but it's not particularly difficult. And it may be a good addition. It depends, of course, on what you do. For sure, if you are attending an engineering program or an applied science program, you need some background in computation, automatic computation that goes beyond Excel. So this may be an opportunity which I wanted to share with you. Okay, we are not saying any further information about this, but if you are interested, just let me know. I'm fully willing to provide additional information and support you. Okay, now we can go back to the list of our lectures and move to the next one, the Earth system. The next one will be climate models, which is basically what is, it is not the conclusion, but it is our first target. So trying to understand how we can develop a mathematical model for climate to make prediction on the future climate. But before passing to climate models, we need to understand something more about the Earth system. And then I will make reference to this presentation. Just 1 second, I look at the chat, okay? Okay, nothing here. Okay. So, the Earth system. The Earth system means the whole of nature, of our planet life, and our planet state, our planet composition. The Earth system is typically studied by geosciences. And the geosciences include all the disciplines that I mentioned in our conversations so far. It includes climate science. It's an essential body of geosciences. It includes hydrology, water cycle, another essential body. It includes tectonics. It includes also in its extended configuration, planetary sciences, because studying the other planets helps us to better understand the state and the science of the Earth system. So Earth system sciences or geosciences are our interest. Why do we also need to describe the inner of the Earth? Because it has an impact on climate through volcanic eruptions, through the magnetic field, through also the tectonics, the movement of the tectonics plates, and why we also need to study planetary sciences, because also the impact of meteorites, asteroids, has an influence on climate. In fact, this is one of the hypotheses that we made for the evolution of Mars from a planet with water, possibly with life, with an atmosphere, to the current configuration. Maybe the fact that the magnetic field changed, as I mentioned to you in our first lecture, maybe the fact that it was hit by asteroids that changed the inclination of the axis. By the way, if you study Mars, or if you get information on Mars, you will learn that there are a lot of craters in the surface of Mars, which are the results of the impact with asteroids and meteorites. And these craters are visible because Mars doesn't have an atmosphere. In the state of the Earth, instead, the craters are, some of them we recognize, that in the past we have recognized some craters due to the impact with asteroids. By the way, the impact of asteroids is a possible explanation for the extinction of the dinosaurs, and it's a real concern. And why it is a real concern? Because in Mars, where there is no atmosphere, we can see several of these craters, meaning that in the long term, during billions of years, it is a significant hazard. It is something that is probably unavoidable. So we can predict that for the next billions of years, also the Earth may be subjected to the impact of big asteroids, which may completely change the configuration, may originate indeed some very harmful consequences. And this is one of the reasons why we study planetary sciences, because nice, bad thing is that probably we are already able to predict the impact of an asteroid with a longer lead time, with a long lead time, like months or maybe even years. And it is a good thing, but on the other hand, it's also bad because, you know, if we are told that in 10 years from now we are hit by very big asteroids, First, there is not much that we can do to avoid it. Second, it's the impact, the real impact is difficult to predict. And third, it's not a good perspective. Anyway, so far we know that in the near future there is no this risk, but this clarifies why also planetary sciences are important. But let's focus on our problem. Our problem is to describe climate. And then I said, let's consider also the Earth system. And how can we study the Earth system, which is very complicated. It includes, as I said, many sciences, but many components. So there is a modern view. The modern view is towards interdisciplinarity. The modern view is holistic. Holistic means that we try to model, to understand, to focus on a problem or a system in a comprehensive way by looking at all the implications. So when we say, I want to adopt an holistic approach to my studies, means that we are not studying one exam by one and say, okay, now I focus on science of climate change. Once I did it, then I look at the next one. But we try to, in our holistic interpretation, to study all together and to try to see the whole, the big picture of your study plan, and not just one by one. Okay, in this way, you can better understand the implications. You can better understand what is the purpose why you are here today to attend a lecture of science of climate change, because you identified what is the connection with the overall structure of your study plan. So this is the modern view to also approach the Earth system. Of course, it requires an interdisciplinary approach, which is not easy. And given that it's not easy, and given that in the past we had less means to study science, then the traditional approach tries to split the Earth system into components. And it is also more understandable. So I will try to start from this traditional interpretation. And the traditional interpretation, basically, let me move to the next slide, and then we come back to this one. The traditional interpretation is to decompose the Earth system into the so-called spheres. Okay, so separate parts. Okay. Here you see, for example, the atmosphere, the biosphere. The biosphere is the domain of the living bodies. Hydrosphere is the domain of water. So we study water, we study the atmosphere, we study the ecosystems separately. And then these spheres compose what you see, the big picture. So if I want to look at this big picture holistically, then I try to focus on the connections between human contribution, atmospheric composition, ecosystem, water quality, evaporation from the ocean. If I want to use the traditional approach, I look at the ocean and I say, okay, let me devise an ocean model. And then if I need fresh water from the land as an input data, input information, I ask an hydrologist, please give me an estimate of freshwater flux from the land. Okay. I mean, the traditional approach, it's from an educational point of view, it's probably more appropriate because it allows to make specific focuses. But don't forget that everything is part of a whole, like we are part of a community and individuals are part of a community. And once again, the Earth system is closed, meaning that only energy can flow in and out, with the only exception of masses that can enter from the space, like meteorites or asteroids. Entities include the dynamic processes that connect the different parts of the system itself. So when we look at the spheres, when we look at the individual part of the Earth system, of course, we cannot neglect the connections. I made the example of fresh water from the land to the oceans, means that I need an input variable quantifying the fluxes of fresh water. And this is a connection between the two systems. It's a flow. It's a flow of an entity, water, from two separate systems, systems that I want to consider separate. So the flow of matter or entities, how they are called here, between the different spheres is something that I need to describe. Okay? And here there is mention to the modern holistic view of the Earth system as a unified whole. Fine. So let me give some example besides the four that I mentioned earlier of spheres. And again, in my web pages, there is a link to a video, another geoscience video that explains the spheres and their connection. So other spheres are the cryosphere, is the domain of snow and ice, cryospheric sciences. To each of these spheres, I go back, we can identify a science. And for instance, atmospheric science, hydrology is the science of the hydrosphere, biogeosciences is the science of the biosphere and the geosphere. Another science of the geosphere is geology. Okay, and then cryospheric sciences, lithospheric sciences is the lithosphere is the domain of the land, and the pedosphere is the domain of the soils, and the science is soil sciences. And then there is a recently introduced sphere, which is the technosphere, and it's the domain of humans. Techno, because we are focusing on the human impact, the human modifications, human-induced modification through technology, of course, because we need some technology in order to modify nature in order to accommodate our needs. Now, when we look at the spheres individually, we can also say that we adopt a reductionist approach, which is the opposite of the holistic approach. A reductionist view, which means that we reduce our attention to one specific domain. Perfect. So let's now focus on the connections. And in particular, I mentioned the flow of matter between spheres. And let me give some examples of these matters. And of course, in order to get an holistic view, we should describe all of them. But we can neglect some that are not very important. And for instance, if we are interested in reducing our emission, we can focus on the carbon cycle. And so one possibility indeed is to look at the carbon cycle. And I think here there is a sketch of the carbon cycle. Okay, so you see energy from the sun feeding the vegetation, and the vegetation creates energy sources, carbon stored in plants and soil microbes, and also fossil feedstocks like petroleum, coal, natural gas. These are produced, these fossil fuels are produced by the energy of the sun, as I mentioned in my first lecture, through the work of vegetation. And then, of course, these fossil fuels, if you look at the arrow here, they can be converted into fuels like petrol, electricity, and chemical products. Through the emission of CO2, we get energy at the end of the story. And they can be used in transportation, industrial production, in producing electricity. And then you see here these electric lines, blah, blah, blah. And then you have the net atmospheric emission. Once again, the CO2 in the atmosphere is obtained by the plants, and then the cycle starts. This is a cycle that has its own time scale. You understand that the time scale of conversion from solar energy to fossil fuels, it's a very long time scale. We try to accelerate it, or in a bit to accelerate it, to speed it up by CO2 injection. You may have heard that this is a technique that has been explored recently to take CO2 from the atmosphere or to take CO2 from industrial emissions and pump it in the underground in exhausted oil reservoirs. So when we pump out oil from the soil, we free some space in the underground, and we use the same pumps to inject back CO2 with the hope that we accelerate the process, because of course we don't inject organic material, we inject already carbon. But there are still some doubts on the effectiveness of this process. First, because there is the feeling that CO2 may leak out through cracks. Of course, oil may not leak through very tiny cracks, but CO2 in the long term, instead of finally producing again fossil fuels while it's still a gas, may leak out. And second, it's not really, we are not really sure that it works in this way. So that the storage will be finally feed again the carbon cycle in the way it was naturally conceived. So, of course, focusing on the cycle is a way to connect the technosphere with the atmosphere, with the pedosphere and the geosphere. It's a way to look at the connection. This is a possibility. Another possibility, interesting, is to look at the water cycle. The water cycle is a connection among all the spheres. And here you don't see the technosphere, but indeed it is connected. Because, for instance, for the production of hydropower, you see many similarities between the water cycle and the carbon cycle. What is a striking difference between these two cycles? And a striking difference. It's not the spatial scale because it's global with local implications. So in terms of spatial scale, it's not a big difference. The big difference here is the time scale. The water cycle is much quicker, much quicker. So for instance, water vapor is a significant greenhouse gas, but the residence time of water vapor in the atmosphere is much lower than the residence time of CO2. There is a much rapid exchange. And indeed, this cycle here is much faster. There is also a deep component of it. Deep groundwater. This may take like, some people say, very deep groundwater, like 300 meters, 400 meters, where we can get with wells. Some people say it may take like 10,000 years to renew, to be replenished. But 10,000 years, it's a long time for the human scale. But it's nothing compared to the time scale of the carbon cycle. In order to form fossil fuels, it takes much more than 10,000. So here the time scale is a big difference. And it is something that you have to consider when you build a model, of course. Because when you describe these fluxes means normally matter divided by time. So the time scale is extremely important. So the unit of a flux is matter divided by time. We call it flux because it describes a movement. And the movement is described by velocity. Okay, when you want to describe the movement of a fluid, the only thing that you need to define is the velocity vector. So velocity means that time is extremely important. So the water cycle is, once again, here you don't see the technical part of it, but it is, of course, extremely important because humans use water, we draw water, like groundwater, we use it, etc. Energy exchanges is another way of looking at the connections, and it is extremely important and very difficult to describe. All of these cycles I'm talking about, keep in mind, there are several uncertainties. Even when we talk about human emissions are estimated with a huge uncertainty. We cannot have a method to measure human CO2 emissions. You understand that it's really, we can get proxies like the CO2 concentration in the atmosphere, but still there is uncertainty. We cannot attribute everything of CO2 in the atmosphere to humans only. And even when we talk about energy, we have an estimate of average solar radiation, but then these exchanges between the soil, land, atmosphere interaction depend on the water cycle, depend on the carbon cycle, many things, and it is indeed, there is uncertainty. This is an interesting diagram which reflects an estimate. So this diagram clarifies what are the energy exchanges in quantitative terms. Of course, they are estimates with uncertainty. And let's start from 100, which is the conventional unit, the conventional amount of energy from the sun. Okay, and you see that this 100 for 23% is reflected by the clouds into the space, and then 47% reaches the ground. 4% is absorbed by clouds, and 19% is absorbed by the atmosphere. So the unit 19 absorbed by the atmosphere. And then if we look at the atmosphere, we see that there is a flux of 98 from the atmosphere of energy to the Earth's surface, and a flux back of 49. So it means that the atmosphere irradiates a quantity that is equal to 147. So it means that the atmosphere has to receive 147, because in order to emit 147 needs to receive 147. Where is this income? It is from the Earth's surface to the atmosphere is 104. From the sun directly to the atmosphere is 19. So the total is 123. And the remainder 24 are taken by clouds, 4, and let me see, sensible heat, 5, and there is still something which I can't recognize here. Understanding this diagram is always difficult for me, but the balance, if you look at the balance of the red arrows, which means energy from the atmosphere to the surrounding, this has to be compensated by the energy that gets into the atmosphere by the sun, by the absorbed by the clouds, and reflected by the surface. Probably is the 7 here reflected by the surface that we have to consider, and also the 23 reflected by the clouds. So everything should be in balance, and this gives to you an idea, okay? And from this, you can also see that the atmosphere plays a relevant role, because the total of the fluxes to the Earth is comparable. So from the atmosphere to the Earth, the flux of energy is comparable to the total income from the sun. So it is indeed very significant. So looking at energy exchanges may be another way to understand these connections. When you build a model of the Earth system, your model, of course, it's limited to some of these components, may be limited to some of these components. We are still not able to build a digital twin of the Earth system. So when we build a digital model, usually we focus on a sphere, and in some of the cases, we may only focus on an element, like for instance, hydrology focuses on modeling the water cycle. So only water. Of course, hydrology also needs some input in terms of energy in some of the cases. Okay. So Earth system dynamics. So what is the behavior that we expect for this system? Okay, we already mentioned many interrelations. We already mentioned very complex dynamics. We already mentioned tipping points. An important behavior that we are expecting that we didn't mention so far is non-linearity. So today we discuss non-linearity and then we close. What is non-linearity? You know, when I was a student, my PhD advisor already very often mentioned to me, this is highly nonlinear. I didn't understand what's the meaning of that. And keep in mind, when I was a PhD student, it was not so easy. It was not so easy to go to Wikipedia. There was no web. And therefore, my feeling was, okay, I want to understand what is nonlinearity. What is the textbook that I should consult? I didn't really understand. Keep in mind that my background was engineering, civil engineering. So there was not a strong focus on mathematics. Yes, there was, but not really in the implications. So what is nonlinearity? He was keeping saying, this is nonlinear, it's nonlinear. So it's extremely important because it's extremely dangerous, it's nonlinear. So actually, it is very simple. When I looked at it, I understood it's very simple. So first of all, in mathematical terms, a linear function, a linear relationship between two variables is something that you draw with a straight line. Okay, so to make it easy, if I say temperature is linearly dependent on altitude, which is to some extent true, it means that if I draw in a graph temperature, dependent variable, altitude on the horizontal axis, independent variable, more or less the relationship is a straight line. Okay, this is the linear relationship. If it is a composition of two straight lines, it's already nonlinear. Okay, so if I do something like this, again, temperature and altitude, capital H. Okay, this is linear. This is non-linear. It's piecewise linear, it's called. So it means the single pieces are linear, but the composition is non-linear. So this is a very simple explanation of linearity. Why it is convenient? Why linearity is exciting? Because, let me just change this graph. Okay, this is non-linear. Because if I stay on the linear part of it, once that I understood it, it is very easy to make a prediction of change in temperature after a change in altitude. It's very easy, and there is no surprise. But suppose that I don't know this dashed line, and I get here, suddenly I say, gosh, this is a surprise, because with a very small increase of temperature, I get a jump in, very small increase in altitude, I get a jump in temperature. This is a surprise. If I thought that it was linear, instead it is not. So a linear function, a linear relationship is more easily predictable. It's no surprise. It's nice. And also the model is simple. A straight line, those of you who have a background in very simple math know that it's a model which is described by slope and intersection. That's it. That's it. But in mathematical terms, look on the screen now. How can we define a linear relationship? Two conditions, very easy. First, let's suppose that we have a function linear of two variables, fx plus y. We can decompose it in fx plus fy. This is also called the superimposition principle, or in Italian, principio di sovrapposizione degli effetti. It means you have a contribution by x and a contribution by y. The result is the sum of the two contributions. Two separate effects, you sum them, superimposition. Second condition, if you have the relationship between x and one multiplier, the result is equal to the multiplier times the result fx. These are the two conditions that must be satisfied to make sure, in mathematical terms, that you have a linear relationship. And the linearity, as I said, is very nice. Problem is that the Earth system is nonlinear. In linearity, dealing with uncertainty is easy because the superimposition principle makes things very easy. Non-linearity means that if you have a perturbation plus a tiny one, the result may be the result of the perturbation plus a magnification of the tiny one. This can be non-linearity. Non-linearity means that a very small perturbation causes a disaster. This is non-linearity. So we have to get into nonlinear models. Questions? Okay, good. So, thank you. See you in presence next Monday. Grazie.